All right, over the next few videos, we're going to try to do some example problems of resolution that mimic real life situations to help you understand how to apply Rayleigh's criterion formulas. But before getting going, why don't we just try to do a little thought experiment at home so you can actually see resolution in action. Okay, so the first thing I want you to do is get a piece of paper, and then I want you to draw two black lines that are separated by 2 millimeters. It helps if you draw with like black ink rather than pencils because it's hard even to see the regular lead pencil lines. So try to make two black lines with felt that are about 2 millimeters apart. Make those lines as straight as possible using a ruler. Put them on a piece of paper and then tape them to the wall. Then I want you to step away from the wall and be really honest. Move away and then try to see when you can just stop seeing those two lines clearly distinguished from each other. They'll start to get blurred into each other, okay? And then measure that distance from the wall and where you're standing, okay? Record that distance. And then what we're gonna try to do is we're gonna try to actually calculate using Rayleigh's criterion what that actual distance would be in a perfect situation. And let's compare. Let's see how well your eyes are compared to theory, okay? So how can we apply Rayleigh's criterion to this situation? Well, Rayleigh's criterion says that the minimum angle of separation, that angle over there, corresponds to 1.22 times the wavelength of light that's being reflected off of those lines, divided by B, which is the slit width of the pupil of your eye. Now, why 1.22? Because the hole in your eye is circular. So remember, this is due to circular diffraction from the last video. So the diffraction maxima are separated by a larger distance. It's by 1.22, a factor of 1.22. So this is for circular diffraction. That's why we have that. Okay, and what I've drawn here is the diagram of the situation. Here, although they're white, these would be the black lines that you put on that white piece of paper, and they're separated by 2 millimeters. And X would be the distance that would be the maximum distance we can go before we can't resolve this anymore. Now, if I increase that distance, what happens to this angle? As I move my eye away, like for example over here, we can see that that angle, okay, I'm just going to draw the pupil here, but we can see, just so you guys understand, I'll erase this in a second, but if I go a further distance away, okay, the angle gets smaller, okay? So the angle of separation, if I draw this as a white line here, that theta prime is going to be less than theta when it's closer. So as I move closer to the objects, what I'm going to be doing as I move my eye closer is I'm going to be increasing the angular separation. Okay, as I move further and further away, the angular separation gets smaller and smaller and smaller. That's why it's going to be harder to see. We're going to have a limit as to how far we can move before that angle becomes too small. Okay, it becomes smaller than theta min. So that theta min, based on that formula, will limit how far I can be from these lines before that angle becomes too small. So let's just go back and get rid of this eye and those dots. Maybe it'll be faster if I do that. All right, that should be good enough. Okay, and so what we're going to do right now is we're going to try to calculate what that distance is going to be based on this formula. So there's a few assumptions I need to make before I'm going to do that. The wavelength of light, how do I know what wavelength of light when we're looking at just regular light in a room? Well, all different lamps that you have in a room have a spectrum, okay? So they have a whole variety of wavelengths, but you'll have a maximum, I'll have a maximum wavelength, okay? So if this is my intensity and that's my wavelength, I'll have a lambda max, a maximum wavelength based on light. So we're just going to assume that my eye is going to be interpreting the maximum wavelength of light that's coming from light from a room. And in this case, I'm just going to assume that it's 550 nanometers. Oops. Okay, so let's draw that out. So my lambda is going to be 550 nanometers. And what is the slit width of my eye? Well, in a regular position, you would imagine that the pupil is going to be no more than about 3 to 5 millimeters. So let's just say B is equal to 3 millimeters in this case. Now, these are not SI units. I need to convert them into SI units, which is meters. So that's 550 times 10 to the minus 9 meters. And that's going to be 0.003 meters. Okay, I need to have them all in meters in order to be able to calculate theta. And remember, the theta that you're going to be calculating is in radians. Okay, because you are applying that arc formula where S is equal to 2 millimeters. Okay, that arc length. This is going to be my radius, which is going to be x. All right, so we need to understand that S divided by x is equal to theta, okay, which in this case is going to be equal to 1.22 lambda divided by b, okay? That's the relationship that I've developed. Okay, now what I'm trying to do in this formula is I'm trying to solve for the distance that my eye is away in order to resolve this, okay? In order to do that, I have to isolate my distance. So I'm gonna move x to this side, and I'm gonna rearrange and put everything on that side so I can isolate for x. So S times B divided by 1.22 times lambda is gonna be equal to x in this formula, okay? So if I start plugging that in, 0.002 meters times 0.003 meters divided by 1.22 times 550 times 10 to the power of minus 9 meters should give me x. Okay, so let's slowly do that. Let's get my calculator out. Okay, then you guys can pause this and calculate it for yourself. Let's see if we get the right answers. Okay, now remember, it gets kind of difficult. Often kids will set this up absolutely normally, but not get the right answer because, again, you're dealing with scientific notation. Okay, and how do we put that in our calculators? So be really careful. Use the appropriate buttons in your calculators. I'm using my iPhone, which is not a great idea, so that I might not get the right answer. So let's see here, 1.22. Okay, and my answer, x, is equal to 8.94 meters. Wow. So Rayleigh's criterion says that if the light is 550 nanometers, I can be standing almost 9 meters away from the wall and still see those two lines distinguished. Were you able to do that? Let's see if you were able to do that in practice.